Good morning. All right, I want to start with something that has, on the face of it, very little to do with eternal inflation, but it will come up. And just think of it as a side comment before we even begin. It has to do with quantum mechanics, and in particular the foundations of quantum mechanics, which I may or may not come back to toward the end of these lectures. But there was one particular point that I wanted to make, because it will come up later today in, I think, an interesting way. It has to do with the phenomenon of decoherence. Decoherence is a phenomenon which is very important to the interpretation of quantum mechanics. It has to do with when the virtual realities in the wave function become turned into real realities, objective realities, by the phenomena of, sometimes we call it measurement, or sometimes we just call it entanglement between the system under consideration and possibly some environmental degrees of freedom. And then when those the environmental degrees of freedom might just be a big detector, or it might just be a photon which interacts with Schrodinger's cat and carries off the record of whether the cat was alive or dead. It's when that happens that we say the virtual realities that are encoded in a wave function get turned into objective realities. In older language, it's when the wave function collapses, when the wave packet collapses. So all I really wanted to say about it was the following. Imagine a laboratory. There's a laboratory moving upward in time, and experiments take place, phenomena happen. The entire laboratory, if it's a sealed laboratory, is in some quantum state, and it remains in a quantum state, and at no point does the information as to what occurred inside that laboratory get out unless something escapes from the laboratory. A photon, for example. It's that photon which is carrying off a record. For example, it could be a record of whether Schrodinger's cat is dead or alive. It could be a record of whether a photon went through an upper slit or a lower slit in a two-slit experiment. If there happened to be a detector nearby, that detector might detect the photon, and then, forget photon. The detector might detect an electron going through the two-slit experiment, get excited, and then radiate a photon. And it's in the process of radiating that photon that the irreversible phenomena happens that we call wave function collapse. If the photon doesn't get radiated, then the wave function of the entire system doesn't collapse, and we would say, as far as the entire system goes, it remains in a pure quantum state, and there's no record of what happened. It's important to the interpretation of quantum mechanics that decoherence happens, or entanglement between the system and the environment. Is entanglement or decoherence an irreversible phenomena? In practice, when you have a big detector of some kind or a big apparatus with so many degrees of freedom, when a record is left on it by some experiment, in practice it is irreversible. It's just too hard to reassemble all the degrees of freedom and have them go backward and recohere Schrodinger's cat, so to speak, in a linear superposition of states. But in principle, one can imagine mirrors that radiate or that reflect the outgoing photons that carry a signal, that carry a record of a system, bring them back into the system and recohere it. In other words, the wave function which collapsed uncollapses. Now, it is important to the interpretation of quantum mechanics that at least some decoherence does happen, so that you can say that things really happened, really did decohere. And the question is, what is the mechanism for that? Well, the mechanism in ordinary thinking is photons which just come off and never come back. But you can never be sure that there really aren't mirrors way out there which could bring them back together. In inflation or in eternal inflation or in de Sitter-like spaces, there's another mechanism which can absolutely ensure that the phenomenon of decoherence is permanent and cannot be undone. And it's the existence of horizons. If here's the Sitter space and here's our experiment, that entire experiment takes place within a causal patch, and when a photon passes out through the event horizon, it is gone. It cannot come back. And that is a mechanism for absolute irreversible entanglement or absolute irreversible decoherence to take place. And I just wanted to mention it because it is going to come up again. It's going to come up in our discussions about eternal inflation. All right, so that was minus first step of my lecture today. What's that? Say it again?
Is there quite the opposite phenomenon in ADS, where photons get
Exactly so. ADS is a cosmology where nothing ever permanently decoheres, just because its walls are reflecting, right? Okay. Yeah, so let's come back. I think I mentioned the problem that we're going to attack today and discuss today. It's the problem of determining what kinds of different things there are that we would call eternal inflation. There's not just one phenomena. There's a range of phenomena that are controlled by a control parameter. In general, there will be many control parameters. The control parameter in this case would be the decay rate for bubbles to nucleate in a background de Sitter space. So here's the setup. We imagine a potential. We imagine a scalar field potential of some kind. For simplicity, I'm going to take one of the vacuum to have absolutely zero cosmological constant, and the other one to have a positive cosmological constant. Tunneling transitions can take place, and those tunneling transitions that take place produce bubbles. A bubble, without worrying too much about the fine detail that happens right at the bubble nucleation, simply looks like an outgoing light cone, and let's examine it a little more closely. The bubble, the interior of the bubble, and let's give these places names. Let's call this the live place, and let's call this the dead place. Why is this called the dead place? Because it stops inflating here. Inflation takes place here, no inflation takes place here, and I'll imagine that inflation is live, meaning it can reproduce. It reproduces, interesting things happen, expansion. This is dead, inflation has stopped happening. Of course, real life can't exist here, and real life possibly could exist here. So we're not talking about life as we know it, we're talking about inflation. Inflation takes place here, we'll call it live. Okay, now, here's what we're interested in. Yes, as I said, if the potential barrier in between is high, then the basic phenomenon which happens is bubble nucleation. And bubble nucleation, let's take a look at what the diagram looks like fairly precisely. Let's do a Penrose diagram. All right, so we start with the Penrose diagram of de Sitter space. A bubble nucleates at some point. Let's put that point over here at r equals 0. That's arbitrary. Any point in space could be rotated around until it's r equals 0. That's the nucleation point, and after the bubble nucleates, it starts to expand with close to the speed of light, and so it moves out about like that. Well, that's not the end of the diagram. Something happens afterward, and to understand what happens afterward, you go down here to the dead region and you say, okay, that's going to be basically flat space, zero cosmological constant. So we draw a Penrose diagram for flat space. That's what flat space looks like. This portion of the diagram was misrepresented as de Sitter space, but let's patch into it the corresponding piece of flat space. Here's the domain wall going out. Here's the domain wall going out. Notice that r is equal to 0 over here. R stands for the size of the two-sphere that's attached at every point to this diagram. And it goes to infinity up here, monotonically. Likewise, r is equal to 0 over here. R is equal to infinity over here. Likewise, monotonically. And so this can always be matched by a little bit of squashing and squeezing. This can always be matched onto here. And now we have a picture of a bubble of dead vacuum nucleating in a live vacuum. What we're interested in is the global behavior of this and the statistical structure of the pattern of nucleation of bubbles as a function of a control parameter, which we're going to take to be, let's say, the height of this bump here. When the height is very high, the bubble nucleation rate is very slow, and bubbles are widely dispersed and far from each other. Eternal inflation takes place, as we discussed last time. As the barrier comes down, bubbles nucleate faster and faster. At some point, the bubbles will nucleate so fast that they will simply fill up the whole volume, and the live vacuum will be extinguished. It'll become extinct. No inflation after a while. In between, there are several phases, several different statistical phases of eternal inflation, all of which are interesting. And in fact, given that we are in a vacuum which descended from eternal inflation, which may be wrong, but given that we are, we don't actually know which of these phases we live in. So it's worth exploring what the various phases are. Okay, the control parameter is gamma. Remember what gamma was. The decay rate per unit space per unit time was gamma times h to the fourth, where h is determined by the height of this potential over here. It's a dimensionless number, and basically we can think of it as going from 0 to 1. It's the probability that within a Hubble volume, within a Hubble time, a bubble is nucleated. In one Hubble time, in one Hubble volume, it's the probability for nucleation to take place. And the question is, what happens as we vary gamma? Okay, so let me begin drawing another diagram here. Let me divide up space into causal patches. Let's have an initial condition over here. The initial condition will be that the vacuum is in the live sector. And now let's just, these are guidelines. They're not real phenomena. They're guidelines. And they divide the initial surface into causal patch size regions, or horizon size regions, regions of size H inverse. As time goes on, let's draw more of them in such a way that we fill the space-time. Over here at this point, we have more causal patches, or more of these little wedge-shaped objects, and as time goes up, the number of them exponentially increases. In any one of these, a bubble could nucleate. Now, just for simplicity, really just for simplicity, let's assume that the bubbles tend to nucleate at these points, or at this point, or at this point here. You don't have to assume this, of course. Where I'm going is I'm going to make a simple lattice model of what happens. All right, so just for simplicity, let's place the nucleations, but they could take place in between. That's not important. And when a nucleation happens, it creates one of these dead regions. There's a dead region. Here's another dead region. Back here, a bigger dead region. Bigger in the sense that it looks bigger on the coordinate patch. Up here, a very late one will look small. And if you wait long enough, this system will fill up with bubbles, in such a way that it forms a fractal in the future here. We're interested, as I said, in classifying the different statistical behaviors that you would see if you looked down from above at this bubble nucleation. The trick is to cut it off. We can't study the entire infinite structure all simultaneously, so what we do is we cut it off at a given time. We look at the bubble population that would be formed by all bubbles before that time. That gives us a pattern of bubbles, and then we let the cutoff go to infinity, thus creating smaller and smaller coordinate patch bubbles. Right? It looks like a statistical system, not that unfamiliar from other areas of physics, where there are big things, smaller things, smaller things. And that's the structure that we want to understand. All right, to do that, I'm going to make a simplified model. The main reason for studying this model is because in totally different contexts, it has been completely solved by mathematicians. It's called Mandelbrot percolation theory. And the two regions, the dead regions and the live regions, are called the curds and the whey. Somehow this has to do with the making of cheese, but I don't know what it has to do with the making of cheese. Cheese, when it's made, is full of little fractal bubbles, I guess. I don't know. In any case, here's the model. Instead of these these diamond-shaped regions, we're going to slice through it at any given time, and we're going to divide space. Here's a region of space, a region of coordinate space, and we're going to begin by dividing it up into cells, each cell about horizon size. Right? And just to make the model very concrete, we're going to do it on a square grid. Actually, a cubic grid, a cubic grid. All right, so we start with a cubic grid representing this initial state here, broken up into cells. Okay? All of the cells start live. That's a boundary condition. We could start some of them dead, but let's start with them all live. And so they're all colored. Now at Stanford, we had great problems deciding whether we should call the dead regions white or black. We started calling them black, but then I started drawing them on the blackboard and coloring them in with white chalk, and we got very confused. So we will use the terminology live and dead. Okay, so everything starts out live, which means white, which on the blackboard means black. All right. What is the probability? Now we decide in each box whether a bubble nucleates there or not. If a bubble nucleates, and it nucleates with probability gamma, each one of these boxes is imagined to be horizon size. We're going to also discretize time, and the time step is also going to be inverse h. That means that the probability to nucleate a bubble is just gamma. So with probability gamma, we either color this dead or we don't color it dead. Probability gamma is the control parameter for this system here. All right, after going through the first round, this corresponds to all of the bubbles that are nucleated in the first round, meaning the first E folding or the first two folding. We then break up the boxes, the remaining boxes, into things of half the size, which means each box is broken up into 8 new boxes. You can break up the dead ones also, but the dead ones are dead, and they don't care whether they're broken up or not. They're finished. They're out of the picture. And then we go through the remaining live part of the lattice, again, with the same probability gamma, coloring it in, killing it, or not killing it, and so forth. Whatever's left over, we divide up again. Now, this dividing up is, of course, inflation. If we instead draw the picture at each stage so that each box is Hubble size, of course, the entire picture has to grow exponentially. Since I can't draw pictures that grow exponentially, what I'll do instead is break things up into smaller and smaller boxes. Okay, this is the inflating region. This is the dead region. And the first question is, what is the probability that the entire thing gets extinguished? It could happen that in the first step, everybody is colored dead. There's a probability for that. All right? If it happens, it's extinguished. But it might live for a while. It might live through several steps. Is there a probability that it will live forever and continue to inflate? And the answer depends on gamma. So let's see if we can work it out. Here's the equation I'm going to write down. Let's follow a particular trajectory through here, concentrating for the sake of just expediency, I'm also going to divide up the dead regions. The dead regions are dead, they don't reproduce anymore, but I'm going to divide them up just for counting purposes. First question is, how many boxes are there after the nth step? And the answer is easy, it's 8 to the n. 8 to the n. Each doubling takes each box and multiplies it by 8, and so we get 8 to the n boxes altogether after n steps. Now, imagine following a trajectory that wanders, at each step, wanders into a box, and ask what's the probability that that box is dead? The probability, or what's the probability that a given box is either live or dead? In particular, let's take the probability that it's live after n steps. Oh, incidentally, the probability that it's live is equal, by definition, to the number of live boxes after n steps divided by the total number, which is 8 to the n. Okay, so the probability that it's live satisfies an equation, and the equation is p live in the n plus first step, right, for a given box is, first of all, the probability that at the nth step, its parent was live. Let's see. Minus gamma times p live. That's it. Why? Why minus gamma? This is just basically the probability that it gets killed. If it gets killed, it's no longer live. So it's 1 minus gamma. To make it simple, it's 1 minus gamma times p live. We can also write an equation for p dead. I'm not going to use it, but let's write it anyway. P dead, we don't need it. P dead of n plus 1 is equal to p dead of n plus gamma times p live of n. Notice the sum of these stays equal to 1. If p live plus p dead is 1, then it's 1 over here. These cancel. We don't need the second equation. The first equation is all we need. It's easy to solve. At each step, you get a factor of 1 minus gamma. You lose a probability of 1 minus gamma. So after the nth step, the probability is 1 minus gamma to the n that you're still live. Okay, that says that the probability that you're live goes to 0. Sounds like you're extinguished. But no, the number of the probability is the ratio. If I want to know the number, the absolute number of live cells, I multiply by 8 to the n. This is the number of live cells at time n. It's if n live goes to 0 that it becomes extinguished, not if the probability for a given cell. Okay, what's the condition that the system remains alive forever? The answer is that 1 minus gamma times 8 should be bigger than 1. If 1 minus gamma times 8 is bigger than 1, then the population will exponentially increase. This will be exponentially increasing. If it's less than 1, then the average population goes to 0. Let's see, I think if I remember that you get extinguished if gamma is bigger than 7/8. So that's the first fact. And the point 7/8 in this example corresponds to the transition between no eternal inflation and eternal inflation. That's where it occurs. We can calculate something else in this model. I'm not going to do it. It's a little bit intricate, but it can be done. It can be worked out. It's just basically algebraic equations. You can calculate the probability that eternal inflation takes place. Now, eternal inflation will definitely not take place if gamma is bigger than 7/8, and it has a finite probability of taking place if gamma is less than 7/8. We're starting with a single box. As I said, it's always possible that the single box can get killed in the first step or the first two steps. So there's always a possibility of extinction. But the question is, what's the possibility or probability of no extinction? And that's the situation for gamma less than 7/8. And when it's calculated, it's of course 1 when gamma is equal to 0. And it smoothly goes to 0. Smoothly goes to 0. The fact that it smoothly goes to 0, the people who study these kind of statistical problems, Mandelbrot and other mathematicians, call this a second-order phase transition because it's smooth. In the language of eternal inflation, this transition is the transition from no eternal inflation to basically slow-roll eternal inflation. It's the situation when the decay rate is large. In other words, when you've pulled the height of this barrier down low enough that you're just at the edge of where eternal inflation takes place, and the eternally inflating side of it is what's called slow-roll eternal inflation. All right? Now, there are two more phase transitions as a function of gamma. Let's plot gamma over here again. This is gamma going from 0, let's say, to 1. We found one phase transition, but we're going to find more phase transitions in here, characterizing different kinds of behaviors, which is quite different than what happens in slow-roll eternal inflation. All right, to explain it, I need first to explain a concept called percolation theory. Percolation theory is a standard statistical mechanical problem, and it goes something like this. We're not going to iterate for the first round. Just ordinary percolation theory does not subdivide the cells after they've been subdivided. You just start with a big, let's say, infinite lattice. An infinite cubic or an infinite square lattice. From now on, I will not draw cubic lattices. I will draw square lattices. You start with a big infinite square lattice. Here it is. It extends in both directions, in all directions. And you randomly, with probability gamma, either paint it with chalk or leave it blank. In other words, in the current terminology, you kill it or you leave it live. But we're not going to follow it yet as it breaks up into smaller pieces. We just want the pattern of things that are created. If the probability is small, if gamma is small, then on the average there will be a large separation between these clusters of dead regions. In particular, if the probability is very small, the typical cluster will be no bigger than one cell, and they'll be very well separated. Now, as you start to jack up the probability for transition, there's a notion of cluster size. There's a notion of percolation clusters. Here's the idea. If you haven't percolated, percolated means these things get connected together in a big infinite network. If you haven't percolated, then it is possible to run a surface, a two-dimensional surface, but I'll draw it as one-dimensional, through the whole lattice from one side to the other, even though it's infinite. you'll always be able to find a place to put that surface. If these two clusters have grown together, never mind, go around it here. There'll always be a way to run a surface. And so we could say we characterize the phase here by saying there exist crossing surfaces that cross the whole geometry which stay completely in the live region. Let's call them live crossing surfaces. Live crossing surfaces, LXS. There also, of course, exist live crossing curves. That's obvious. If you can send surfaces from one end to the other, you can put lines in them and make curves. So the characterization of the percolation for small gamma, and it's the order parameter which characterizes it, is the existence of live crossing surfaces. Now we increase gamma. The percolation clusters on the average begin to grow. The typical connected cluster will grow. And if we follow the average size of a percolation cluster, it will smoothly go to infinity. The percolation clusters will run into each other, they will get bigger, and the average percolation cluster will grow. In fact, its size will grow as you go to some particular value of gamma. I think it's a gamma somewhere is about equal to a third. It's not exactly equal to a third. And at that point, the clusters will grow together and percolate. Okay? But when they percolate, they don't completely fill up the entire geometry. What happens is the percolation clusters interrupt the crossing surfaces, but they don't interrupt the crossing curves. You can still find curves through it, and I'll tell you roughly what the percolated region looks like. The percolation region is kind of an infinite network of tubes. These things connect together to form tubes, and it looks something like this. If you start with a collection of lines like that, and then fatten them, now take away the lines. And now extend this out to infinity and create an infinite network of tubular structures like this. In here is the dead region. Out here is the live region. Okay. You can also have disconnected dead regions over here. And you can have buried in the solid mass of the dead region, you can also have some live regions. But the characteristic is the existence of this infinite network. And when that happens, the network interrupts the live crossing surfaces, but it does not interrupt the live crossing lines or the live crossing curves. You can still have curves go through this from one end to the other, but not surfaces. So that's a new phase. That's the second phase. It begins at about a gamma of about a third, and the dead regions, which might be the regions where life is possible, incidentally, form these big tubular networks. Anything else to say about them? And that persists for a range of gamma. Now, this model happens to be symmetric between black and white if you interchange gamma and 1 minus gamma. Remember, all we're doing is painting a cell white or dead with probability gamma. We could do exactly the same and start with a completely white thing and paint the thing black with probability 1 minus gamma, and it would be the same model. So there's a symmetry at gamma equals a half. At exactly gamma equals a half, it is completely symmetric between live and dead. And that's an interesting fact. And in fact, gamma equals a half is in this phase where you have these tubular structures. It's called the tube. Yes, Edward?
Why isn't the symmetry broken by the fact that once you die, you can't die again?
No, we're not doing the iteration yet. We're not doing the Mandelbrot sequence of iterations. This is just a one-shot deal so far. Conventional percolation. Is that the answer? Yeah, okay. Right, so we're going to come back to that, but once you die, well, first of all, once you die, you don't come back to life. Once you die, you're in a terminal vacuum that's no longer inflating, and the assumption is that when you're in a terminal vacuum, you don't come back to life. Okay, so here we are, live, dead, tubular structure, and that tubular theory is correct right at gamma equals a half. That's an interesting fact because it's not entirely apparent that this tubular infinite structure throughout space is symmetric between the live and dead regions. But in fact, there is. It is. There are, for example, cycles in here. There are cycles around here. And this tubular topology, the tubular topology like this, is symmetric between live and dead. It's tubular with respect to live, and it's tubular with respect to dead. So there's a phase in here which is tubular. That's just a name that we made up at Stanford. I don't know what the professionals call it. Okay. Now, what happens beyond gamma equals 2/3? Well, white and black. Let's give this one a name over here. Let's give this one a name. Let's call it the dead island phase. Dead island. Before we get to the tubular phase, we have islands of dead region. Islands of dead region. Let's call this the live, no, it's the dead island phase, DI. Dead island between here and here, and it means that the regions which have stopped inflating form connected small clusters. Sometimes we call them pocket universes in the eternally inflating world, or bubbles. They could be colliding bubbles. They could be bubbles which collided, but they form a connected cluster. Okay, so that's the dead island phase. But now guess what happens when you move over to here? By the symmetry, there's a live island phase over here. That phase would have the property that it has islands of live stuff. Now live and dead just mean the two colors in this diagram. So far, we're not iterating it. Okay, so that's the phase structure. Symmetric about a half, tubular in the middle, dead island on one side, live island on the other side. Okay, now let's consider the next step where we start breaking this up and undergoing the iteration which allows us to mock up eternal inflation. All right? So we go to the next step, and then the next step, and the next step, and the next step. I'm going to tell you what mathematicians know about this. At each step, after each step, the pattern is the same. The only difference is that these points move somewhat to the left. The fact that they move to the left is obvious. When you go to the next round, you're going to put more dead stuff in. You're going to make it easier to percolate. Right? If you start over here with no dead region, and you undergo one round, you find out that the transition is at about 1/3. If you add more dead stuff in the next round, it will clearly push this point to the left. And it will also push this point to the left. It's no longer symmetric. Everything gets pushed to the left here. That's what would happen if you went through 2 iterations. If you go through 3 iterations, you push it a little more. If you allow the system to run to infinity, you push these points to some finite convergent places so that in here you still have dead island phase, in here you have tubular phase, and in here you have live island phase. But there's another phase, and the other phase is the extinction phase. If gamma is bigger than 7/8, then extinction. This is the phase diagram then. Can that be read? If it can't be read, I'll read it. Dead island out to some finite gamma, tubular in between, and the next is live island phase. Now, the nature of these transitions, this transition over here is second order. That's what I showed you before. That's this curve over here. These transitions are now first order. Let's go back to the standard percolation for a moment, where we don't iterate and make things, chop them up into smaller and smaller regions. Let's keep with the original percolation model. The original percolation model, all of the transitions are second order. What that means, what is a second order transition? A second order transition is one in which the correlation length becomes infinite at the transition point. That's the definition of a second order transition. The correlation length is just the average size of the percolation clusters. What happens as you increase gamma is the percolation clusters grow, they begin to get connected together, but before they actually form the tubular phase, the typical percolation cluster grows and becomes infinite. Right? That's a second order transition. Something else happens which is different in this Mandelbrot sequence of percolation theories. So let me show you, let me give you a rough idea of what it looks like. Let's start in the dead island phase. So we have some dead islands with some value of gamma so that you have dead islands. Now, that's the first round. The next round, when you subdivide the lattice and add in more dead stuff, may make these dead islands somewhat bigger, but it'll also create small dead regions here in between. Go a little more. Go to the next step. The next step, in other words, the next iteration, will make a little more structure on here. They may collide. If they collide, it'll make some structure. And there are lots more smaller islands. At some point, before the typical large percolation cluster gets infinite, they become connected together by the small structure in between. That's what happens. The transition happens suddenly. All of a sudden, this cluster, which is of finite size, suddenly finds himself connected to this one by the kind of microstructure of small bubbles in between. Small bubbles mean late-formed bubbles. So it will generally happen that that percolation happens suddenly in the Mandelbrot construction, and I would say in eternal inflation. When you decrease the rate of bubble nucleation, you'll go through a transition, which will take you to the tubular phase. In fact, it does inherit the tubular kind of phase, but the tubular phase is now constructed out of tubes which have all kinds of microstructure. It's hard to draw. Tiny, tiny filaments connecting things. It's hard to draw. I'm not going to try to draw it, but it maintains the tubular structure in the next, between here and here. And then it maintains the white island, sorry, not the white island, that's an old term, the live island structure in here. Okay? But with first order transitions in between. Now, the easy thing to understand is the dead island phase. You just form bubbles of decayed vacuum. All right, that's this famous picture which people are always drawing. The bubbles can collide, that's okay, but they form distinct, separated things. This is what's usually analyzed. Sometimes people analyze it from this side. They study the potential when it's close to slow roll inflation, and then they find the transition across here. That's the transition from extinct to live island. This transition would be hard to find by any methods that weren't discrete like this. Perturbation theory or solving stochastic equations, perhaps, I don't think it would be easy to find this transition or this one. All right. So, any questions about this? No. You should have questions about this. Nobody has questions about this? All right, I have a question about this. What does the live island phase actually look like? This is the phase in which the inflating region forms islands. What happens in those islands? All right, the live regions are susceptible to a phenomena called cracking. Cracking is a term that the people who do this kind of mathematics use. And what cracking is basically that it's unstable in each round of the sequence of the Mandelbrot sequence, either this Mandelbrot sequence being the subdividing of the lattice into smaller and smaller lattices. It's unstable with respect, this is dead, this is live. You create more dead stuff, and it's unstable with respect to these regions cracking by creating dead region in between them. The dead regions, the live regions get cracked into non-inflating regions, and it keeps happening. At any given stage, there's always live stuff left over, but the live stuff keeps getting cracked and cracked and cracked. So the question is, what does this cracking look like? If you think you live in this island phase, or this phase of island eternal inflation, or slow roll eternal inflation, it would be important to know what the dead region looks like and how this phenomena affects it. So I'm going to show you the simplest example of cracking and show you what it does. And it does something, I think, spectacular, extremely interesting. It creates something that I think every relativist thought could not be created. So let me show you what it does. Let's start with de Sitter space. Let's take a space-like surface through it. It's a sphere. And now let's imagine something which would be extremely improbable if the decay rate was small. But if the decay rate is pretty large, it's not that improbable. Namely, a whole bunch of bubbles, this is of course a 3-sphere, not a 2-sphere. A whole bunch of bubbles nucleate, connected together, separating the left side from the right side, separating this region from this region over here. Now, I've drawn it as a kind of chain of beads, but of course, in higher dimensions, it would be a surface. It would be a surface of nucleations that would separate one 3-dimensional region from another 3-dimensional region. That would be a crack. We start with everything live, and a crack forms that separates the geometry into two inflating regions with a region in between of non-inflating. So let me show you what that looks like on the Penrose diagram. This 2-sphere, this is on a 2-sphere. This chain of pearls is not a chain, it's a surface of pearls on a 2-sphere. Here's a 2-sphere. Let's put the 2-sphere over here on the Penrose diagram. Every point on the Penrose diagram is a 2-sphere. And once it forms, it starts to grow. It starts to spread. It starts to thicken. The wall or the region in here starts to thicken, and so it thickens out like that. It eventually hits time equals infinity. Now, what's in here, since it corresponds to no cosmological constant, what's in here has to be a solution of the vacuum Einstein equations. It is a solution of the vacuum Einstein equations. You might think it's just some sort of flat space, but it's not. It's a black hole. It's a Schwarzschild black hole, an eternal Schwarzschild black hole. This is the picture that you draw, or the top half of the picture that you draw, to study the eternal black hole, which is, of course, an unphysical thing usually. You can't form one of these in the usual way. What you form is basically half of it, normally. Well, you know the picture. Where is it? Whatever. You form this eternal black hole which has a singularity in the middle, two flat regions, one over here and one over here, separated from each other. They cannot communicate with each other. They're separated by this region in between. A singularity forms, and everything in here is a solution of the flat Einstein equations, although not empty space, Schwarzschild black hole. The most important thing is that the crack is accompanied by a singularity, so that when a crack occurs, there's the crack, a singularity forms in between. Now, the constant cracking here, the continuous cracking, is much more complicated. I don't know how to follow it. I don't think anybody knows how to follow it. But the expectation is that the cracking sends out signals that eventually collapse the entire dead region in here. Instead of the dead region persisting, the dead region appears to, all these cracks between different dead regions lead to an instability, or it's expected that they lead to an instability. And so while the live regions continue, they get cracked smaller and smaller, but they remain, and they continue to inflate, they continue to spit off dead regions, but any given dead region probably undergoes collapse. That's the expectation. You can't live forever, even though there's zero cosmological constant out here, in here. You probably can't live forever in this geometry. The dead regions eventually collapse. It's an extremely complicated phase. Nobody knows how to analyze it, and therefore that's the main reason why we don't study that phase, why eternal inflators like to study this phase. Let's talk a little bit about the tubular phase. What would life be like if you happened to be living in the dead vacuum? Yeah. What?
Why that region?
Say it again.
Why that region form a singularity? Why you find?
Well, you have to patch something in here that's a solution of the vacuum Einstein equations. Okay? You have to patch in something which is a solution of the vacuum Einstein equations. There aren't very many solutions of the vacuum Einstein equations which have spherical symmetry. All Penrose diagrams are spherically symmetric, and it's just a matter of a little bit of mathematics sewing in here a solution of the Einstein field equations. The thing that fits in there, the only thing around is Schwarzschild black holes. One possibility is a Schwarzschild black hole of zero mass. Right? That's not what happens. A Schwarzschild black hole of zero mass would not have a singularity. What does happen is the Penrose diagram of a Schwarzschild black hole. I didn't intend to go through this. You can find this in the literature. It's, if I remember, I'll write down the references to it. I think it was first discovered by Sasaki and his co-workers in Japan. It was rediscovered by our group at Stanford and Berkeley. And you can read about it. The main point, though, is that, I'll give you a reason why, yeah, let me try to explain. Yeah. Okay. Let's suppose a singularity didn't form. I don't know, something like that. Let's go from here, right through here, back to here. The size of the two-sphere over here is infinite. Right? We're up near the boundary of de Sitter space. The size of a two-sphere is infinite. So let's draw the two-sphere right about over here. It's very big. The geometry is very big over here. It's very big over here. And in here, the metric is finite. And so that means a throat through there. A finite geometry. Basically, this geometry looks like two big geometries connected together by a narrow throat. This is an unstable situation. This is called a wormhole. It's a feature of ordinary general relativity that wormholes are not stable, they collapse. And that's what's going on here. This geometry just slicing right through here would be a wormhole between two very large geometries, and it would collapse. Okay, so this geometry I don't know how, or this cracking phase I don't know how to analyze. The tubular phase is a little bit easier to think about. It does not appear that it's unstable. There's no reason to think it's unstable. But it's kind of interesting to think about what an observer who was in this tubular phase would see. Now, he'll only see this if the cosmological constant is 0, and only see it if he has much better telescopes than I think we're ever going to have. But still, here's what well, let's first go to the island phase. Let's start with the island phase. Here's the island phase. And an observer at the center looks out. He looks out, looks back on his backward light cone, and from any given time, let's say he's looking at some surface of constant time, he sees a surface. This could be, for example, looking at the surface of last scattering. He sees a sphere around him. As time goes on, that sphere, he sees more and more of that sphere. More and more of that sphere. If the cosmological constant is really 0, that observer can live forever and look back and eventually see the whole thing. So with time, he sees a surface that spreads out and eventually fills the entire geometry. What about some person in here? What would they see? They would look out after a small amount of time and see a surface of last scattering look like that. Go a little bit further in time, see a surface which looks like this. As time goes on, start to see a surface which looks like this. A little more time, and this surface will spread around here. Eventually, these things will cross, and they'll be able to see right around the universe. This is a phenomena which is common in topologically complicated universes. And so with time, you'd eventually be able to see this whole tubular structure, and not only the tubular structure, but its topology, by seeing multiple images on the sky. Now, don't go out and try to do this. We don't live in such a world, or at least we don't live in a world with a vanishing cosmological constant. The implication of not having having a non-vanishing cosmological constant is you only get to see so much growth before you encounter horizon problems and so forth. So this is what you would see if you lived in this tubular phase. In the island phase, what you just see is a sky, a spherical sky around you, and you see more and more of it with time. Okay, so those are the phases of eternal inflation in a very simple model. If the model is a lot more complicated, for example, many minima, then the structure is very much more complicated. As Alan Guth says, in an eternally inflating universe, anything that can happen, and it will happen an infinite number of times. If there are regions on the landscape which allow the tubular phase, and we started nearby, we might see a region in, let's call it the multiverse, which looks tubular. In other places, we might be controlled by some other kinds of decays which look more island-like. And so there would be patches of space with all these various different kinds of phases taking place, and the whole thing is a horrible mess. It's not easy to classify. I have no idea how to classify it. The main reason I'm telling you this is to tell you there is more than one thing called eternal inflation. It is not one thing, it is many things. Most of them highly intractable. Okay, any questions about the topological phases of eternal inflation? Yes?
If you travel to the Sitter space, which would also be possible, would also singularity fall?
I think so. Yeah, yes. I think you would just form a de Sitter black hole. Yeah, I think the answer is yes. So let's see. You start in de Sitter space, and you tunnel not by one tunneling event to de Sitter space, but you create this surface or shell of tunneling events that looks like a two-sphere. And then I would guess that I'm pretty sure what you'll create in here will be some sort of de Sitter black hole. So yes, I think the answer is yes. If you tunnel to de Sitter space, by this phenomena of surface cracking, yeah, you will still have singularities. Any other question?
How do you determine the mass of this black hole?
Say it again?
How do you determine the mass of this black hole?
Oh, all right. Well, it depends on, I don't remember the answer in detail, but I do remember what the parameters are. The parameters are how high up it nucleates and the size of the critical bubble wall. And I don't, for the life of me, remember the connection. It's a good question. I don't remember the connection. I think the bigger the domain wall, the bigger the critical bubble here, the larger the mass of the black hole. But I can't remember the details, so I won't try to reconstruct them.
What is the difference in predictions of eternal inflation and other kinds of inflation?
We'll come to that, I think. We'll come to that. Eternal inflation is not a substitute for slow roll ordinary inflation. Let's get that straight. Let's talk about that for a minute. Bubble nucleation like this typically makes an empty universe, a universe with nothing in it or very little in it. This kind of tunneling event is not an interesting candidate for making an observable universe, an observed universe. What you need, which is rather Baroque, you need something very complicated in order to make a viable picture out of this. You need that after you've tunneled out, and we're going to discuss the structure of bubbles, but for now, just let me say it quickly. What you need is after you've tunneled out, then you have to settle down on a plateau. So it would look something like this. You tunnel out, but after you've tunneled out, here you're in the, you've tunneled out to about over here, and then in here there's a region of inflation, slow roll inflation, before you roll to the final cosmological constant over here. So eternal inflation, which takes place in these regions over here, is not a substitute for ordinary slow roll inflation. They are two different things. In fact, you could characterize them this way. To make slow roll inflation, you need a degree of fine tuning to make this potential flat enough. That's not what you need to make eternal inflation. What you need to make eternal inflation is just minima. The sharper the minima, the better. The more likely you are to stay in that region. So they're quite different phenomena, and they are not substitutes for each other. You might ask, why do we need eternal inflation? I don't think that's the issue. I think the issue is to say, start with a given theory, do we or don't we get eternal inflation? That's, if there are lots of minima out here, even just one more minimum out here, you will get eternal inflation. Even more than that. I would say there's a reason to believe that eternal inflation has to be in our description of things. And the reason is the existence of the current cosmological constant. The current cosmological constant will lead, if it really is a cosmological constant, in other words, if it really is a stable minimum, it will itself lead to eternal inflation. It's enough to make eternal inflation. Just being here. Just having one minimum makes eternal inflation. Incidentally, a world with just one minimum like this is not a viable world. It's a world which will come to thermal equilibrium at the bottom of this well, and we'll just sit there and sit there and sit there. Let's not. I'm getting too many things thrown in altogether now. What I want to do is study a generalization of this model a little bit now. This is an interesting generalization which represents a complicated landscape. But I'm going to study an example in which there's a complicated landscape which does not have anything but positive energy vacuums. Again, that's not a viable world, but let's just study it and see what kind of things come out of it. It has lots of minima. They all inflate. Some inflate faster than the others. And transitions are possible between them. A network of transitions. I want to equip that model with enough complexity that it can study a multiverse that would be produced by such a complicated landscape. All right, this is not too hard to do. You just say every box can have any number of colors. All boxes are alive because they all inflate. All boxes are alive. None of them terminate the eternal inflation. And you just give them many colors. The colors represent the different vacuums here. And you can play exactly the same game. You start with the whole checkerboard, three-dimensional checkerboard, painted one color, the initial condition, whatever it happens to be. We could start here. And then let it run. Tunneling events recolor some of the boxes with various probabilities. Let it run a little more. Running means subdividing the boxes into sub-boxes. And red boxes can make transitions to blue boxes. Blue boxes can make transitions to green boxes. Green boxes can make transitions back to red boxes. You allow for the possibility that not only are there transitions down, but you allow the possibility that a freak accident can happen and allow a transition up. And you write a bunch of rate equations. Rate equations determining the probabilities for each color of box as a function of time. Okay, let me show you what those rate equations look like. They're intuitively, more or less obvious. Let's define PA to be the probability that a box has the 8th color. Let's define it to be the number of boxes after a given number of iterations. In other words, at the nth stage, it's the number of boxes of type A divided by the total number of boxes. All right, let's consider the rate equations for the evolution of PA. And I'm going to write them down. Yeah, here they are. PA at the n plus first step. All right, this is the probability that this box has color A after the n plus first box is, first of all, the probability that it's inside a bigger box of the same color previously, in the previous step. That would be what you would write down if there were no transitions. Now, if there are transitions, you have to add to that, I'll write it down, summation over B, and I'll tell you what they mean, minus gamma AB PA. Now, let me tell you what that is first. The minus sign means depletion. You start with the probability that it was in the 8th kind of box and that it made a transition, that the smaller box that you're interested in made a transition from A to B. So you read gamma AB this way. This is the transition probability for A to B. Transition from A to B is gamma AB. That's a probability, pure probability, times the probability that the previous box that it was embedded in has color A. All right, so that's depletion. And then there is replenishment. Replenishment would be also the sum over P of gamma AB PB. So this is the probability that the previous box was of a different color, B, and that you made a transition from B to A. That's it. Those are the rate equations. The input are a set of gammas, and you solve them, and you determine what the population and what the probability of a given box looks like as a function of time. Okay? Let's work on that a little bit. First of all, the linear equations for the P's. They're linear equations with a matrix. The reason I've put those summation signs in there is because these equations are not amendable to Einstein's summation conventions. Here we sum over, let's see, where is it? Yeah, here we are not, this is not summed over A. It's the probability that we're in the 8th box times the transition from A to B. So Einstein's summation convention doesn't work very well for these equations. The right-hand term is okay. We sum over B. The left-hand side, we do not sum over A. We sum over B. In other words, we sum over all the things you could get to from A by making a transition from A to B. Nevertheless, these are linear equations, and there's a matrix structure connected with them. The matrix, let's see what the matrices look like. The first term is diagonal. It's the probability A being proportional to the probability A, PA. All right? So what we have in here is on the diagonal, we have, let's see if I have written down somewhere. We have gamma 1, 2 plus gamma 1, 3 plus gamma 1, 4. That's all on the diagonal here. The diagonals are big. They take a lot of room to write. Transition from 1 to 2. Do I have that right? This is, no, yes, no, yes. With a minus sign. This is depletion of the first vacuum by nucleating the second, depletion of the first vacuum by nucleating the third, depletion of the first vacuum by nucleating the fourth. Then in the next diagonal here we have minus gamma, let's say 2, 1, minus gamma 2, 3, I think, and so forth and so on. And that's what the diagonals are built like. The off diagonals are simpler. They're just gamma AB, and I think this one is gamma 2, 1, and this one is gamma 1, 2. Now, these matrices are not symmetric. Incidentally, what we're interested in is the eigenvalues and the eigenvectors of this matrix. If we know the eigenvalues, we know the rates at which the eigenvalues control the rates at which the probabilities change. All right? The eigenvectors, those are the stable sort of equilibrium configurations. In particular, what we're going to look for is an eigenvector with 0 eigenvalue. An eigenvector with 0 eigenvalue is a stationary state that doesn't change with time. Eigenvalues of this matrix over here. You can shift the first term to the left-hand side. We shift the first term to the left-hand side and call it, oh boy, I can't reach it. Okay, in your notes, erase the PA of n and call it delta PA on the left-hand side, the change in PA from one step to the next. That's equal to the matrix on the right-hand side. If you know the eigenvalues of the matrix on the right-hand side, you know the rate or you know the evolution of the P's. So the problem is to compute the eigenvalues of this matrix here. Now, how do you even know it has eigenvalues? It's not a symmetric matrix. How many eigenvalues does it have? Does it have n eigenvalues? Does it have no eigenvalues? Okay, there's a trick to make it, what does this act on? This acts on a column vector, P1, P2, P3, P4. If you use the principle of detailed balance, then you can convert this to a symmetric matrix. What is detailed balance? Detailed balance is a relationship between the decay rate of 2 to 1. Sorry, this is 2, 1. It's a relationship between the decay rate from one vacuum to another versus the decay rate in the other direction, or the transition rate in the other direction. These transition rates are not equal, but they're related by detailed balance. So let me tell you what detailed balance says. Detailed balance says that gamma AB is equal to a symmetric matrix, MBA. This could be the quantum mechanical transition amplitude times a factor, and the factor is the density of states. Let's write it as e to the entropy of the final vacuum B. Each of these vacuums has an entropy. The entropy represents, the exponential of the entropy represents the degeneracy, or represents the level density. It represents the number of states associated with that de Sitter space. And this is what detailed balance says, that the gammas are not symmetric, but there's a symmetric matrix which you multiply by the density of final states to find the transition matrix. If you do this, this is now an exercise. I want you to do this exercise. If you do this and you write, let's see if I have it written here correctly. And you redefine, you write that PA is equal to e to the SA over 2 times phi A. In other words, you rescale the PAs by a factor of e to the SA over 2. Rewrite this not for the P's, but for the phi's. You will find that the matrix in here magically becomes symmetric. So that's an exercise to show that these rate equations, become symmetrized. The symmetric matrix appearing in them is MAB, and all the factors, non-symmetric factors here, disappear for phi. That ensures that there's a complete set of eigenvectors. All right, so that's the first part of the problem. The second part of the problem is to find one of the eigenvectors, to prove that the matrix after redefinition, or it doesn't matter whether it's after redefinition, the matrix here has a 0 eigenvalue. Prove that it has a 0 eigenvalue and find the eigenvector. 0 eigenvalue means a state, and all other eigenvalues, incidentally, are negative. That means that the other eigenvectors decrease with time. A negative eigenvector in these kind of rate equations indicate a decrease in time. A positive eigenvector would correspond to an exponential increase of probabilities. That's impossible. Probabilities can't be bigger than 1. And a 0 eigenvalue is a excuse me, would be a stationary probability distribution. There is, yeah.
Excuse me, but isn't it okay? Because if you add all those of the matrix, you will get 0. So it's like, well, it's clearly determinant is 0. Right?
It's clearly what?
Determinant is 0.
There is a 0 eigenvalue. Yeah, the problem, yes, it is obvious. But the problem is to find the eigenvector. Okay. All right? And I will tell you what the eigenvector is, because the eigenvector is interesting. The eigenvector is that PA is equal to e to the SA. You could plug it into this equation here. You just make this substitution. You don't need to symmetrize the equation. You do need to symmetrize the equation if you want to discover there are a complete set of orthonormal eigenvectors. But just to discover this fact, all you have to do is plug into here, and you'll discover that this eigenvector here, in other words, e to the s1, e to the s2, dot, 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 that's an eigenvector. Of course, it's not normalized. These e to the s's are huge. You have to normalize it if you want the total probabilities to add up to 1. And what this statement is that if you choose the probabilities to be equal to the density of states or to the number of states in each de Sitter space, that's a stationary solution. It persists forever. It doesn't change with time. In fact, because it's the biggest eigenvalue, all the others being negative, whatever you start with, you will tend asymptotically to this eigenvector. All the others exponentially go to 0 with time. So whatever initial state you start with, if you wait long enough, this will be the population of the different vacuums. What is this population? This population is thermal equilibrium. It's thermal equilibrium where every state is populated with equal probability, basically. Every state on an energy surface is with equal probability. It's what you might expect if you had a landscape like this, and the landscape point, the configuration point, was hopping around in here ergodically. If it was hopping around in here ergodically, in other words, equal time and equal volumes of phase space, this is what you would get. This is thermal equilibrium for these de Sitter patches. In other words, if you follow this Mandelbrot construction, moving along from one box to the next box in time, to another box, to another box, to another box, and it doesn't matter what route you take, just take a route through the time evolution of it, from a box to a box inside that box, to a box inside that box, to another box inside that box, what you will find is that after a while it settles down to an equilibrium configuration, which is just thermal equilibrium. This is not a good thing. This is not a good thing because it's not consistent with our world. Our world is not thermal equilibrium. There are transients and so forth. But worse than that, it says that every state is populated according to equal probability. A world like this would be a Boltzmann disaster. It would be a world in which the only things that happen are fluctuations away from equilibrium, and our world is not a fluctuation away from equilibrium. It's not a viable description of the universe. It's a universe that's full of Boltzmann brains. What's wrong? How do we fix it? We fix it, presumably, hypothetically, this is what eternal inflators think, by having terminal vacuums, dead vacuums of either 0 or negative cosmological constant which can't recycle. In that case, this procedure breaks down. There is no detailed balance anymore. There is no way to go from the dead vacuum back to the live vacuum. You can still write down the rate equations, but the dead vacuum just doesn't recycle. You can still write down the equations. We're running out of time, so I won't write them down now. I'll maybe write them down next time. And you can still solve them. But instead of finding, there is still a stationary state. Can anybody guess what the stationary state is now? Everything dead. Just everything dead. Solid mass of dead vacuum. That's all it would be. In other words, a solid mass of this, no transients, just everything has all right. So that's not what we're interested in. Our world, incidentally, is not a dead vacuum. Our world has a little bit of cosmological constant. It's still live. So a solid mass of dead vacuum is not what we want. What we want is the transient to that. So in other words, you look at the next leading eigenvalue, of slightly negative eigenvalue, and that corresponds to a transient which exponentially decreases in probability. The probability exponentially decreases with time, right? But it's a transient. Transients can have interesting things happen during them. You're going from one vacuum to the next vacuum to the next vacuum to the next vacuum, and then eventually getting into the dead vacuum. But during the course of popping from one to the next to the next to the next, interesting things can happen. So, and it's, as I said, it's not I guess you would call it a stationary behavior. You wouldn't call it a static behavior. I'm misusing terminology. Thermal equilibrium I would call static. A flow of a system as a system that flows from one thing to the next thing to the next thing. Here's an example. You put a ball in here, it jumps down to here, jumps down to here, jumps down to here. You keep putting balls into here and they keep jumping down one after another. That's stationary. If you keep putting the balls in at a certain rate, that's stationary, not static. Things flow from here to here. If you have a terminal vacuum like this, then the rate equations tell you that the behavior, as you follow, in particular, as you follow a trajectory through this Mandelbrottian structure, you see a flow down, eventually always ending here. But there are always new live regions which create more balls. So what does it look like? It looks like at every stage there is still a source of balls because there are still live regions, in particular live regions up here, anywhere along here. These live regions are eternally inflating, and they're a constant source of supply of balls which roll down the hill. When they get down here, they're finished, they're dead. So that is what things would look like with or without terminal vacuums. Without terminal vacuums, a disaster. You just sit in one of them, or you sit at the bottom from now and then, hopping up and making transitions, but everything being static. Static in the sense that the probability distribution doesn't change. And with terminal vacuums, you have a flow, okay, which is a better situation. Interesting things can happen during flows. Okay, let's see, do I have 5 minutes? There's only one more thing I wanted to say, and it has to do with this issue that I brought up in the very beginning about decoherence. I showed you how when there's a horizon, an experiment can give rise to radiation which passes out through the horizon that way. There's a sense in which this happens in eternal inflation that I just wanted to point out. This Mandelbrot model, or in general eternal inflation, has a tree-like structure to it. The tree-like structure you can see very clearly in this Mandelbrot model. Let's say you start with one box, just one. Think of that as the root of a tree. And then it breaks up, let's say, into 4 boxes or 8 boxes. The tree gives rise to 8 branches. 2 is enough for the purpose of the discussion. Those branches never talk to each other anymore. Once this box has done what it's going to do, it never talks to this box anymore. The reason is, I lost the picture, but it's out of causal contact. They're separate, different horizon patches. They're out of causal contact, so this one never talks to this one anymore. What happens next? Each one breaks up again and again. Each time spitting out 8 branches. Every now and then a branch gets killed. It can no longer branch. That's dead. That one's dead. That one's dead. But the tree keeps growing. Okay? The tree keeps growing. You have 2 ways that you can think about this tree. I'll come back to this decoherence in a minute. But you have two ways that you can think about this tree. You can think about it globally and count the total number of branches. That's this 8 to the n. And it counts the total number of branches of a given type. You multiply PA by 8 to the n to find the total number of branches of a given kind. Okay? Or you can say, look, I am a fellow who likes to travel along branches. I don't like to split up at these branches here. I'm a real observer. I travel along a trajectory through my own causal patch. A single causal patch corresponds to following a sequence of branches along here like that. And in that case, what you see is the probabilities. What is the probability after n branching that you're in a given vacuum? That's P of A. So there's this dual description, global and local. Global, studying the whole tree. Local, following it. In one case, you're interested in the total number of things. In the other case, you're interested in the probability that you're in a given situation. Okay, now let's come back to this business of decoherence. Let's suppose you're one of these observers who follows himself along a sequence of branches. Then what his world looks like starts with the original vacuum. Right? Then a nucleation occurs. That could be this branch over here. So he follows it into this branch. And then another nucleation happens. And then another nucleation happens. And that observer is following his world line through this branching structure, which means following it from one vacuum to another until he finally achieves extinction. Well, not extinction, but just death, until he finally gets to a terminal vacuum, and then he stops. Okay? All right, let's think about a following crazy situation. There's a cat over here. This cat can survive a transition to vacuum A, but it cannot survive a transition to vacuum B. All right? So it's a cat who can live in vacuum A, but can't live in vacuum B. What happens after the transition happens? And the transition could either happen to A or B. What does the quantum state look like? All right, so what the quantum state looks like is live cat, happy cat, times state A, plus dead cat, this is a state, dead cat times state B. This is an entangled state. This is a state in which the cat is entangled with his environment, and in this case, the environment just corresponds to whether he's in vacuum A or vacuum B. Now the question is, does this state decohere? Is there any mechanism to have it decohere? Decohere means that a record is formed of which vacuum you're in, and that record is irreversible. Well, the answer is yes. Let's follow this cat, or this entire experiment, to the end and draw the causal patch. This record of whether you're A or B goes out through the horizon here. Once it's out through the horizon, it can no longer communicate with what's inside. So this horizon has a permanent record that cannot go away of whether the vacuum was a transition to A or B. That mechanism alone would be enough to decohere this state, and decohere it means collapse the wave function from dead cat, from the superposition to either one of these. In other words, remove the coherent phase between these two states. So it's interesting. There is a mechanism in eternal inflation to cause decoherence. It's permanent decoherence. And here's an example of it, how the sequence of bubble nucleations really, in a certain sense, I lost my diagram. I don't have the diagram anymore, but represents the same phenomena in an experiment as the radiation of a photon. Okay, I think we're finished for now. Next time I'm going to come back and discuss the measure problem, try to make the measure problem as simple for you as I can, and to discuss the various proposals for measures on the landscape.